We're starting off chapter 7 by trying to think of different ways to represent sine, cosine, tan, equivalent trig functions. So sometimes we need to use cos, not sine, or use tangent, not cotangent. We have to be able to switch between them back and forth.
The first thing we're going to talk about are the horizontal shift identities. So here we have the parent sine wave here, and underneath I'm going to put a k value in there, sine kx. So Desmos asks me to add a slider. I'm going to do that. And what I want to see is the green one is now on top of the red one, as k changes from 1 to any other value, here we go. As you know, that is a horizontal stretch or compression. What I'm looking for, though, if you look at the title, is I'm looking for a horizontal shift. I'm looking for a value of k that will, whatever the value of k is, it will look exactly like the red one you see here, the parent graph. And there isn't one. There's no value of k that gives me exactly the parent graph again. The only one that does work is if k is a 1, which is the automatic value of k anyway, invisible. Now what about if k is a -1? K is -1? No, that's not the same as the red graph. So that's not giving me, I can't use a value of k to get exactly the parent graph back again. So forget about k. Now what if we didn't have k, if we had one of the other parameters like c? Is there a value for c that would, let's change that color to something else. Is there a value for c that would land that one right on top of the parent graph? No, only a c value of 0 will work. So what I want you to think about is what parameter out of the a, k, d, and c parameters, is there any parameter that when you change it, you can still have the original graph? So if you're thinking about that, hopefully you've come up with the only parameter that will work, and that is d. So let's try sine x minus d, like that. So what value of d will work? There's lots of them. Look at how often the green one is lining up right on top of the red one. So there's lots of values of d that are going to allow it to line right on top. And that's what we're looking for. We're looking for a way to shift one function to make it match another one, because the topic for today is exploring equivalent trig functions. I want an equivalent way of writing sine x. So there's one way to write sine x, and now I've found 6.3. That seems like kind of a random number. Where does that come from, 6.3? So 6.3 is rounded on Desmos here, but it is a number that maybe you're thinking that you recognize what that is. And there are other values as well of d that would work. There's a -6.3, and there's many more. But I only have my scale going from -10 to +10, but because the sine wave is repetitive, it's periodic, I would have an infinite number of possibilities of numbers here. So let's talk about exactly what that d value is.
Other than d equals 0, what values of d translate the sine function exactly onto itself? We found a 6.3. What does that mean? I hope you recognize that as being 2 pi. This says that sine x, the graph of sine x, which is the red one, is exactly equal to, it's equivalent to writing sine of x minus 2 pi, and that's a period or a cycle. So if I take my sine wave and I subtract 2 pi, which is a horizontal translation to the right 2 pi, I'm going to land on the exact same space where I was. I could also add 2 pi. That would be the same thing. And there's lots of options here. I could subtract 4 pi because the period is 2 pi, because that's one cycle. I can add all kinds of multiples or subtract them of 2 pi. Y equals sine x and y equals sine x minus 2 pi are equivalent expressions because one function is a horizontal shift of the other based on its period. The sine horizontal shift identity says that the sine function is equal to adding or subtracting 2, so I've got an n in here. N is an integer. That means I could make that n a 5. Then I would have 2 times 5, that would be 10 pi. So any multiple of 2 pi, adding or subtracting like we did here, 2 pi, adding, subtracting 2 pi, 4 pi, anything will work. If I take this apparent sine wave and I add on a period or 2 periods or 3 periods or 4 periods, it's going to look exactly the same as the parent function. Horizontal shift identities for cosine and tangent are also based on multiples of their periods. It's all the same thing. The cosine horizontal shift identity is the same as sine because it also has a period of 2 pi. And so you need to think about what is the period of tangent. Period of tangent is pi, so if you add a full cycle or subtract a full cycle, you will have an identity. Remember what identity means? It means that one is identically equal to the other. So tan x is identically equal to tan x plus 3 pi, for example. They are an identity. In the next slide, we're going to talk about, instead of comparing sine to sine, cos to cos, tan to tan, what about comparing one function to another function?
Continuing to talk about horizontal shifts, what I want to do this time is take two different functions. These are called cofunctions. Sine and cosine are cofunctions of each other because they're so similar to each other. So what I'd like to do is figure out a way to make sine look like cos or make cos look like sine. So look at the two. The black one is cos and the red one is sine. What would I do? What parameter would I change on the black one, which is cos, to make it line up with sine? Hopefully you've figured out it's the d value again. I need to change the d value in cos. I want cos to look like sine. I'm trying to map it onto sine. What will I need to do? So how much of a shift have I got to put on there? It's got to be a d value, but what is the d value going to be? So if I put a bracket here, x minus what? So if I just put a number like 2, well, that's not right. That didn't line them up. What about a 1? No. So think of radians, of course. We want some value of radians. Let's just delete that again. Pick any point on the sine wave, say right here, this pi over 2 and 1. Now how would I get this max pushed over onto this max? We're talking about a phase shift. Phase shift of what? So in this case, if I subtracted pi over 2, let's see how that looks. Perfect. So that, what we see there is it's another horizontal shift, but it's with a cofunction. So it's between two different functions. Instead of thinking about how could I shift sine to be right on top of sine again, this time I want to get into a different function. So let's talk about the different options here.
What values of d translate the cosine function exactly onto the sine function? We've got this identity right here. Sine x, that's the red wave, will be exactly the same as cos if we perform this transformation. So there's an identity. What about the other way around? How could I make the sine match the cosine? How could I take the red wave? How would I translate the red wave so that it would match the black one? And that's the same thing, but it's just in the other direction. And there's multiple, infinite answers for these values because you could shift over and over and over again. Now that we're done with sine and cosine, let's talk about tangent and its cofunction, its partner function, which is tangent and cotangent.
Continuing on with our cofunctions, this time I want to take these two cofunctions, tan and cotan. They are cofunctions because their graphs are also very similar to each other. Here's what cotan looks like. So how could I get cotan, that's the blue one, how could I make that look exactly like tan? Now in this case it's not just going to be a horizontal translation. If I add a slider in there, it's not going to line up ever. We need something else. We may need a horizontal translation, but there's something else that's going to happen too. Can you figure out what it is? Delete this while you think. Hopefully you've figured out it needs a reflection. Either I can put a negative a value here, that will help it to line up once I put in a sideways shift, or how about a negative k value? That would also work. Remember, because when we talked about even and odd functions, when we put a negative in for the k value or a negative in for the a value, we can get the same result. So this is the parent function for cotan. I'm going to need a reflection, either an a or a k reflection, a negative value there, as well as, let's put a d value in there again, as well as a d value. So two things have to happen in order for me to get cotan to look exactly like tan. And I'm gonna explain this in later lessons. Why do we want them to look exactly the same? But what's the d value? So what's a d value looking like here? Let's get close to 0. Okay, there's 0. There's no transformation, no horizontal translation, and that's pretty close there. That's a 1.6. So decimals is showing us a decimal of 1.6, but of course we are talking about radians here. What is that close to in radians? So let's go back now and get some formulas for this new cofunction identity.
How can we transform cotan to be equivalent to tan? We need either a vertical or horizontal reflection, and we need a shift. So we put those together, and we realize there's an infinite number of ways to write that out. There's a whole bunch of combinations, but here's one. Tan x is equal to cotan x. Now here's the negative. We needed an a or a k, so for this one I put a negative k value, and a shift of pi over 2 to the right. So this is pi over 2 to the right, and this is a negative reflection. This is kind of a messy way of writing it. Usually we write that out like this. So the negative comes into the x, so there's your negative x, and this becomes a positive, and they get switched around. You don't have to write it like this, but this is common for your textbook to have it written in this format. These two are the same. But this is what we have here is another identity. It is a way to say tan is identically the same as cotan if we perform these operations on it. Part C, even and odd equivalent functions. You don't have to remember these titles or part A, part B. I'm just kind of trying to group them together for you in a way that helps you understand it. But when you're done, you don't need to memorize these titles. Here are your functions. The dotted blue ones are your primary, and the solid red ones are your secondary. Well, I want to talk about even and odd. That's symmetry. Remember symmetry? Even symmetry means if we take a function and we reflect it horizontally, reflect it across the y-axis, it will be the same as what our original function looked like. So out of sine, cos, and tan, and of course the reciprocals go with them, do any of them fit there? Cosine and secant, so these ones right here in the middle. Cosine is the dotted blue line, so if I imagine flipping it horizontally, so this point down here gets flipped over, it lands here, right back where it was. So this one has even symmetry, cosine, and then also its secondary partner will have even symmetry as well. So those ones have even symmetry, and that's another way to write one function a different way. Cos negative x equals cos x. So there will be times when we can't have a negative right here and we have to rewrite it another way. We'll get into that later. But today what we're trying to come up with is a whole bunch of different ways to write one function, either translating itself or using another function. Odd symmetry, that's the one with the two reflections. So odd symmetry means it reflects across both axes, or you could think of it as rotating 180 degrees about the origin and then it lands right where it was. Any of these have odd symmetry. The first group here, sine and cosecant, these are odd. Two reflections, put it back where it was. Or you could think of it as one reflection, So imagine this blue dotted line reflecting if you had a negative a value, it all of a sudden reflects down, flips over. That's the same as flipping it horizontally. But same with tangent and cotangent. They are also odd. So we could say that sine of negative x is equal to negative sine x. That's just using this notation right here. Let's try an example. Find an equivalent expression using the related acute angle only for sine of negative pi over 6. Related acute angle. Remember what that means. Related acute angle is, put it right down here, an acute angle is always measured between 0 degrees and what was 90 degrees or pi over 2. So that's acute. And sometimes we pick up the acute and we put it in different quadrants. So the acute of negative pi over 6 is just pi over 6. So the question is telling us we can just use that acute angle of the pi over 6. Right? We have a whole bunch of ways of doing this now. If you think of all the different ways we talked about sine equivalency today, different ways to write sine. There's lots of different ones we've learned already. Let me erase this circle here. And I'll erase all of this. So what I'm going to do is I'm going to use the symmetry, the one that we're just talking about right here on the screen anyway. Using the symmetry, sine of negative pi over 6. So using symmetry, how could I write an equivalent expression? How could I write this a different way? Negative sine of negative pi over 6 is equal to what? Remember that sine is an odd function. So f at negative x, which is what we have here, we have a negative with our x, we have a negative with our the negative k value, negative with the angle. It's equal to negative f at x. So I'm just going to rewrite it like that. These two are equivalent. And just so I can show you that visually what that means, the first one, negative pi over 6. So I'm going to do this one in green here. This is going to be green. Negative pi over 6 is rotating this way, right? Negative pi over 6 would be down here somewhere. That would be negative pi over 6. Now I'm going to put this one in red. If I just did sine of pi over 6, sine of pi over 6 would be here. This is my pi over 6. But the negative in front means I've got to think about reflecting it down. So it goes right where the green one was. So that's how one way to show you how those ones are the same. Part B says secant of pi over 2, and the acute angle is already there. It's pi over 2. So how can I write secant of pi over 2 a different way? That's all it's saying. I want to express it a different way. Secant is an even function. Even function means that we can write it like this. So this is our regular function here. It's the same as taking the function, giving it a negative k value. Or here's an example of what that would look like with cos, but we're using secant. So secant of pi over 2 is equal to putting a negative in front of the angle. That's negative secant of pi over 2. So we're still using the acute angle, but we've made it a negative. Kind of the opposite of what happened over here. We were given an acute angle, but it was negative. We had to write it a different way. So we used that acute angle, and we made the entire function negative. The point of this acute angle is so that you don't say pi over 6, okay, I'm going to say pi over 6 is equivalent to sine of 5 pi over 6. Which that's a different way of writing the same thing. But if the question says, and your homework often does, to use the acute angle, then you can't just go and add on a bunch of rotations and get a bunch of coterminal angles. You have to stick with that related acute. So that's how we can use even and odd symmetry as another way to get an equivalent function, to write a function a different way. We can use symmetry to get that. And yet another way, cofunction identities. This is similar to part A. Recall from grade 9 what complementary angles are. Complementary angles are two angles that have a sum of 90 degrees. In any right angle triangle, the other two angles must add up to 90. So let me just draw a little sketch for you here. If I have a right angle triangle right there, and this corner is 90 degrees, then if this is x and this is y, x plus y have to add up to be 90 degrees because total sum has to be 180. So if one angle is theta, what if I change this x or this y up here to a theta, then the other angle must be 90 minus theta. Except we don't use 90 degrees anymore, we use radians. So here's a representation using theta and radians. If we have one angle that is theta, then the other angle, that's the non-90 degree angle, must be the difference between that, because these two together have to add up to 90, because this one is 90, so the three of them have to make 180, but in radians we're changing that to pi over 2. Okay, where am I going with all this? Let's label these sides, A, B, and C. We know the sine of this angle, sine is opposite over hypotenuse. So sine of theta is A over C. That's grade 10. We know sine of theta for this triangle I've drawn is A over C. But if we look at this angle, and I want to talk about cos of this angle, cos is adjacent over hypotenuse. That's also A over C too. So you can see how we're coming up with another identity. So if sine of theta is A over C, and cos of this angle is also A over C, then we can make the conclusion that this sine theta, that's this left side, is equal to the right side cos of pi over 2 minus theta, because they're both equal to A over C. And if you look back to some of the other ones we've done in part A, you'll see they're very, very similar. When we talked about shifts, we talked about sine and cos being equal if we just shift the wave, right? If we did a phase shift or horizontal translation. So this is another way of coming up with the same thing. It's using the cofunctions, turning sine into cos or turning cos into sine. Now let's look at cos. Up here, this angle, cos, using the letters, cos is adjacent over hypotenuse, so cos of theta is B over C. Up here we did sine of theta, right? But now we're doing, so cos of theta is B over C. How else could I get a B over a C using this triangle? How else could I get a B over a C? And it's going to be with the cofunction, sine. Sine of this angle is opposite over hypotenuse is also B over C. So here's another cofunction identity. You don't have to memorize all of these. Most of these you're going to come up with them as you go along. You can memorize them if you want to, but in math it's always way better to understand than to memorize. So technically you could ignore everything I'm saying and just memorize the things that are in the blue boxes, but then you're not really understanding the math that's going on here. Because another one you have to figure out is tan. How could I do this same process here with tan to get a cofunction? And I think you have that question in your homework, so I'll throw the little formula up there for you, but I believe you have to explore that a bit in your homework. So tan of theta, tan is opposite over adjacent, and that's the same as taking cotan of this angle here. Let's do an example. Use cofunction identities to write an equivalent expression for, we've got two of them. So the clue in the question is we have to use cofunction identities. So I can't say sine of pi over 6 is equal to sine of, and then use sine again. I have to use its cofunction. So I have to write sine in terms of cos. And you have a couple of different ways of doing this already from what we've done in our lesson. But let's look at, first of all, using these cofunction identities. All I'm going to do is, since sine is cofunction is, I have to use a cofunction, its cofunction is cos. I'm going to rewrite this with cos, and I know that sine of any angle is equal to cos of pi over 2 minus that same angle. When I write that out, that means sine of pi over 6 is the same as writing cos of, now I'm copying this down here. So first comes the pi over 2 that was already in the formula, and then I subtract theta. But my theta, the theta that's right here, for me, this is theta, right? This was the theta that was originally is a pi over 6, so I put a pi over 6 here. And now I just have to do a little bit of work with fractions and get a common denominator, which would be a 6. So this is 3 pi over 6 minus pi over 6. I get cos of 2 pi over 6, which reduces to cos of pi over 3. So that means sine of pi over 6 is equal to cos of pi over 3. The next one is sine 5 pi over 16. So that denominator might be a little bit intimidating, but that's okay. We can, I should have given you in the one that wasn't sine again, but that's okay. So we've got sine again here. Actually, let's make that a tan. Tan. We already did a sine one, so let's make that one tan. Tan of 5 pi over 16. Okay, so I look at my formula, I'm looking for the cofunction, so I've got to use this one right here. That's my cofunction. So my theta for this question is 5 pi over 16. That's the theta in the question. So I've got to replace this theta also with 5 pi over 16. So tan of 5 pi over 16 is the same as cotan, bracket. Now I'm writing the pi over 2 minus, and instead of theta, I'm putting 5 pi over 16. And again, I need a common denominator, which will be a 16. So that's 8 pi over 16 minus 5 pi over 16. And I get cotan of 3 pi over 16. So tan of 5 pi over 16 is equal to, is equivalent to, is exactly identical to cotan of 3 pi over 16. And you can always check that out with your calculator. You can put tan of 5 pi over 16 in your calculator, look at the decimal answer you get there, and then try cotan of 3 pi over 16, and you will see the same thing because they are equivalent to each other. Last slide, part E, quadrants and principal angles. So I'm going to go back here to remind you of our quadrants. If I have theta, and theta is going to be an acute angle, so let me draw an acute angle theta right here. There's theta. That rotation up to that arrow is theta. That's my terminal arm. That's theta. And I'm in quadrant 1 here. So this is quadrants. So I'm just reviewing quadrants. Quadrant 1. There's theta in quadrant 1. In quadrant 2, if I took theta and put it in quadrant 2, let me switch colors. So I'm going to take theta, the exact same measurement. Of course, I'm not actually measuring it, but let's pretend I am. And let's pretend that's straight. There's my theta again. This is my theta here, but I've put it in quadrant 2. So now here's my rotation. So I've got theta in quadrant 1 and theta in quadrant 2. That rotation, even though I have no numbers to go from here, I'm going to label around my axes. So this is the same as 0 radians, or it's 2 pi. What was the 90 degrees, now we call that pi over 2. And what we used to call 180 degrees is pi. And down at the bottom is 3 pi over 2. So that new green rotation that I drew, the green rotation is equivalent to writing, it's equivalent to saying pi minus theta. That's this green rotation right here. That's the same as pi minus theta, because if I went all the way down to this axis, it would be pi. All the way here is pi, but we didn't go that far. It's pi minus theta. So that rotation is pi minus theta. And then if we look at quadrant 3 is down here. If I took the exact same angle, if I had measured it, and I was using a ruler right now, and I put it in quadrant 3, right there, there's theta. That rotation all the way there would be the same as saying pi plus theta, whatever my theta is. If theta is pi over 4, then I would take pi and add on pi over 4 to get that rotation. And then the last one is quadrant 4. Quadrant 4. Quadrant 4. I'm putting theta down here in quadrant 4 and rotating all the way around to that. If I kept going all the way, I would have gone 2 pi, but I'm going to subtract theta from that to get that red rotation. So that's theta in each quadrant and how it relates to pi or to 2 pi. If theta is an acute angle in quadrant 1, so if we were starting with the purple one, that's the acute angle in quadrant 1, then the following are true. So going through all the quadrants here, I just want to look at this piece right here, that principal angle in quadrant 1. So sine here, the purple one, everything castrol, everything is positive here. So the purple one is positive here. The green, if I was talking about sine, is sine positive or negative in that quadrant? So this one, remember, was pi minus theta. So is that angle positive or negative? Let me put the castrol on here. C-A-S-T. In quadrant 2, sine is positive. In quadrant 2, sine is positive. That's why we can say, if we're in this is the quadrant 1, this is just our theta. That's quadrant 1. If we put it in quadrant 2, they're exactly the same. Pi minus theta, that's my pi minus theta. They're exactly the same. But if we did cos of the same, cos of this purple angle, cos here is positive. This is positive. But in quadrant 2, cos of this angle right here, cos of that one would be negative. Tan, same thing. So this chart, which again, I do not recommend you memorize, but this chart is just telling you when you take one of it's the castrol, that's really all this is, but it's taking the castrol and it's putting pi's and 2 pi's in here to help you come up with equivalent angles later. So that is what this chart is saying. It's another way of representing cos with cos. So cos with cos. So this is an identity right here. Cos of pi plus theta is equal to negative cos theta. And that's, you could think of that as because it's in quadrant 3, but you could also think of that if you were thinking of the graph, for example. Think of the graph of cos theta being flipped vertically. That's the same as cos having a shift of pi on it. So there are multiple ways of coming up with equivalent expressions, and this is one of them. True or false? Cos of theta plus 2 pi is equal to cos theta. What does that even mean? So I want to talk about this one using this little strategy I'm showing you here. There's lots of other ways to do it, and you probably already know the answer if you're thinking about it with just a horizontal phase shift. You already know the answer, but let's talk about it with this one here. Let's start with the easy part, cos theta. Cos theta. Let me draw a picture. Cos theta is put a principal angle here, right there. There's theta. That's theta. Is that equal to cos of theta plus 2 pi? So this part I put in purple. Now let me switch to blue. Cos of theta plus 2 pi. Cos of theta plus 2 pi means I have to go all the way around. There's pi, 3 pi over 2. There's 2 pi. I've gone a 2 pi rotation, and I want to add theta on there. That is exactly the same. It lands in the same spot. So this is true. Again, you could also think of it with the actual cos wave. Let's say the cos wave is here. That's 2 pi. Now, if I shifted that 2 pi to the left, and I drew a new one, I took this whole graph and I shifted all over 2 pi units to the left, it would land in the same place again. So that's another way to think of it as being true. You can use whichever strategy works best for you. We'll try one more. True or false? Sine of pi minus theta equals negative sine theta. And you could be looking up in this chart and thinking, I just want to find it in the chart, and then I'll know if it's true or false if it's in the chart. Well, it's not really in the chart. This is kind of like it here, right? And this one's kind of like it here. So don't memorize the chart. The chart is just here to show you how to use the quadrants. So using the quadrants, is this true or false? Start with my x and y axis, and let's just draw a theta in purple. Here's theta. The question doesn't have sine theta. Let me, Jane, go to this yellowy color here. Let's draw this first. Negative sine of theta. The negative in front does not mean a negative rotation. It doesn't mean I'm going to rotate in this direction. That would be a negative right here. That would be a negative rotation. What it does mean, and unfortunately in this case it looks exactly the same, but what it does mean is we're thinking of it of flipping it down. It's being translated down. You can think of it like that, as that kind of a reflection. That's negative sine theta right there. Is that the same as, and I'll do this side in green, is that the same as the left side, sine of pi minus theta? Where is pi minus theta? If theta is my purple, pi minus theta would be quadrant 2, right? Remember up here, top left here, pi minus theta is quadrant 2. This is pi. If I subtract my theta, I'll be here. There's my theta. So pi minus theta is that one. So is this rotation the same as this rotation? Are they, and for sine, not for tan or for cos, for sine. For sine, are they going to give the same answer? No, this one is false. And you don't have to use the quadrants to figure that out. You've got a whole bunch of strategies from today. You've got symmetry you could think of, you've got horizontal shifts you could think of, you've got the complementary angles. So we have a lot of strategies to determine if two different expressions are equivalent or not. So lots of little bits and pieces here. If you didn't take very good notes, I recommend you start over again and take good notes. And the second time you watch it, it will make a lot more sense, because everything always does the second time through. So watch it again, take better notes, and then start the homework.